This is a mic check. Can you tell me if the mic is working well or not?
Sure, I can help with that. Could you say a few more words or a sentence so I can check how well your microphone is picking up your voice?
I'd like to believe that it's working, but just give me another confirmation, and we're gonna talk about machine intelligence later.
It sounds like your microphone is working just fine. Your voice is coming through clearly. So let's dive into the topic of machine intelligence. What specific aspect of machine intelligence are you interested in discussing?
Alright, let's assume you are a machine learning expert. I would want to create a machine learning solution that can present and find similar events. I'm not an expert and I've never created anything like this before. So what the situation is that I'm monitoring the blood glucose changes with a continuous glucose monitor, and I get data every 5 minutes. I also log the data for carbohydrate intake as well as burned kilocalories with a smartwatch, with the Apple Watch, and I log the insulin use as well. So there are four variables that I log: the blood glucose values, the carbohydrate intake, the insulin units, and the burned kilocalories. And the events I want to compare are data sets that consists of recorded values of blood glucose during workouts. It can be the case that the user takes carbohydrates before and during the workouts, and taking carbohydrates can increase the blood glucose. But sometimes it doesn't necessarily increase the actual value of blood glucose. It is because the insulin can be so dominant that it can make the blood glucose go down. And exercise only increases the effect of the insulin can have on lowering the blood glucose. The goal is to create a conversation and is to arrive to a moment where we can establish the right logic for creating a machine learning solution for comparing the different workouts and the changes that happen in the blood glucose as a consequence of that. Please help me with this.
Do you have any specific questions or areas where you'd like more detailed guidance?
Yes, I would like to know more about the time series models, especially about time series prediction and time series forecasting methods with respect to blood glucose changes.
Time series models are particularly suited for analyzing and predicting data where observations are collected sequentially over time, like blood glucose levels. Here's a brief overview of time series prediction and forecasting methods relevant to your project. 1. ARIMA, Autoregressive Integrated Moving Average. This is a popular method for time series forecasting. ARIMA models explain a given time series based on its own past values, which includes lagged values, autoregressive part, lagged forecast errors, moving average part, and a differencing step to make the time series stationary. 2. Seasonal ARMA, an extension of ARMA that supports univariate time series data with a seasonal component. This might be useful if you notice patterns in blood glucose levels that repeat at regular intervals. 3. LSTM, long short-term memory. LSTMs are a type of recurrent neural network, RNN, ideal for learning from sequences of data. They can capture long-term dependencies and patterns in time series data, which could be beneficial for understanding complex relationships between exercise, diet, insulin, and blood glucose levels. 4. Profit. Starting with simpler models like ARIMA might be a good approach. As you get more comfortable and your data becomes more complex, you can explore advanced models like LSTM. Would you like more detail on any specific model or aspect of time series analysis?
Yes, please. Give me some detailed descriptions about ARIMA and LSTM as well. I want to know both.
Absolutely. Let's delve deeper into ARIMA and LSTM. ARIMA, autoregressive integrated moving average. ARIMA models are widely used for time series forecasting. They're best suited for univariate time series, like blood glucose levels, where the data shows a clear trend or seasonal patterns. ARIMA models consist of three main components. One, autoregressive, AR part. This represents the relationship between an observation and a certain number of lagged observations. It's based on the idea that past values have an influence on current values. Two, integrated I part. This involves differencing the time series data one or more times to make it stationary. A stationary time series has properties like mean and variance that are consistent over time, which is important for ARIMA modeling. Three, moving average MA part. This represents the relationship between an observation and a residual error from a moving average model applied to lagged observations. The model is usually denoted as ARIMA PDQ, where P is the number of lag observations, D is the degree of differencing, and Q is the size of the moving average window. LSTM, long short-term memory. LSTM networks are a type of recurrent neural network, RNN, particularly well suited for sequential data like time series. They are capable of learning long-term dependencies in data, which is difficult for traditional RNNs due to the vanishing gradient problem. LSTMs have a unique architecture with memory cells that can maintain information in memory for long periods. Key components of LSTM cells are: 1. Forget gate, decides what information should be thrown away from the cell state. 2. Input gate, updates the cell state with new information. 3. Output gate, determines the next hidden state and output based on the current input and the memory of the cell. Applications in blood glucose monitoring. LSTMs can model the time-dependent nature of blood glucose levels. They're excellent for capturing long-term dependencies, like how today's diet and exercise might affect glucose levels tomorrow or later. LSTMs can integrate complex patterns involving exercise, diet, insulin dosage, and previous glucose readings. Both ARIMA and LSTM have their strengths and are applicable in different scenarios. ARIMA is simpler and good for straightforward, short-term predictions. LSTMs are more complex but powerful for capturing long-term patterns and dependencies, which seems crucial in your case, considering the intricate relationships between physical activity, diet, insulin, and blood glucose levels. Is there a specific aspect of these models you're more curious about, like their practical implementation or suitability for your data?
What I want to do is find pairs of workouts that resemble each other, meaning that I would observe the data and specify workouts where the blood glucose behaved in similar manners and pair them up together so that the user can observe the behavior and make it visible.
To find pairs of workouts where the biological responses, such as blood glucose levels, behave similarly, you'll need to focus on a machine learning approach that specializes in pattern recognition and similarity matching within your time series data. Here are steps and considerations for achieving this. 1. Feature extraction. First, extract relevant features from your workout data. This includes blood glucose levels, insulin doses, carbohydrate intake, and calories burned. You might also consider temporal features like the time of day and workout duration. 2. Normalization. Normalize these features to ensure they're on a similar scale. This is crucial for accurate comparison. 3. Distance metrics. To compare workouts, you'll need a method to measure the similarity between two data points. Common metrics include Euclidean distance, Manhattan distance, or more complex ones like dynamic time warping, DTW, which is particularly effective for time series data. 4. Clustering or similarity matching. Clustering. Use algorithms like k-means or hierarchical clustering to group similar workouts. Each cluster will contain workouts with similar biological responses. Nearest neighbor search. Alternatively, you can use nearest neighbor algorithms to find the closest match for a given workout. Algorithms like KNN K nearest neighbors can be helpful here. 5. Dimensionality reduction. Techniques like PCA, principal component analysis, or TSNE can be used to reduce the number of features while preserving the most important information. This makes it easier to visualize and analyze the similarities. 6. Time series specific methods. If you're dealing with long sequences, consider using LSTM networks to encode each workout into a vector. These vectors can then be compared to find similar workouts. 7. Validation. It's important to validate your approach. You could do this by checking if the paired workouts lead to similar outcomes in terms of blood glucose levels, insulin requirements, etc. 8. User feedback loop. Incorporate user feedback to refine your model. Users can provide insights on whether the paired workouts are truly similar in their experience. Considering your application, a combination of clustering for initial grouping and nearest neighbor search for detailed pairing might work well. You'll also want to ensure your model is interpretable, so it's clear why certain workouts are paired together.